Okay, good morning, everyone. I hope you guys had a good weekend. Uh, as usual, please put your questions on chat. Hi, Professor. Hi, Rocco. Good morning. Okay. Excessively cold today. I agree. That's why you guys are all at home, I hope, and staying safe. Okay. All right. So we start. A note about the quiz. Uh, You guys have your grade, of course, and the correction is also on Bryce page. You should be able to look at your quiz and see what you guys did not correct. And if you have any questions, please come to my office hours. So I sit there waiting for you, but nobody shows up. Please use them even on Zoom. Don't shy away from, showing up on Zoom. Uh, Something happened. Some student did use extra like ChatGPT or something to do the quizzes. It will not do you any good if you actually try to cheat on the quiz because your exams will be in the testing center. Your exam will be no calculator, no cell phones, no smartwatch or anything. So please be honest with yourself because it's not going to help you if you guys use anything but yourself to do the quizzes. I can't do much about it, but you will be losing. You are the one who will lose if you don't do the right thing. All right. Do you guys have any questions before I get started? Very well. So you don't have any questions. So what I'm going to do is we will do number 11. I'm going to do two problems based on the idea of area under the curve. And this is, while I'm doing it, I will tell you exactly what I'm expecting you to do. So last time, the main thing we saw is that if we have the following situation, we have a curve like this, and another one, I don't know how it looks like. And this is the point A, and this is the point B. And I'm interested in finding the area between the two curves. Our idea is that we cover the region with a rectangle. So every rectangle, these are the rectangle we cover the region with, typical rectangle, and we choose them to be very, very, very thin to cover the region. We evaluated the area of every rectangle and we came up with the formula for the area. And it was the integral from A to B of the upper curve minus the lower curve, which represented the length from here to here. We multiplied it by the dx. So that's really what we did last time. So today we are going to have two problems along those lines and then proceed. So I will do the following. I'm going to do first number 11 from the book, and then I will do another one. All right. So number 11 was the following. They gave us the region. So they give me the following region. Uh, like this. And this y equal 6 over x squared plus 1. And they give us another region. And this one is y equal 3x squared. Okay. And the question is find the area in between. All right. How we are going to find the area. The formula is easy, but sometimes I will ask you more than just the formula. I will basically, a lot of time, will ask you to walk me through where the formula comes from. So let us repeat the process we did last time. The first thing we did is we want to cover this region into pieces. So to cover it into pieces, we have to think about which interval we have to divide. Okay, that's the interval we have to divide. To be able to find the interval, we need the intersection point of the two curves. So first, we are going to start by finding the intersection point. So intersection point. Okay, how do we find the intersection point? Quickly. How did you guys find the
As
intersection?
equations equal to each other.
Right, we look for the x that makes the y's from both equations the same. So we will set 6 over x squared plus 1 equal 3x squared, and we solve for x. All right, so now the easiest way to solve here is we cross multiply. So this will give me 6 equal 3x squared times the quantity x squared plus 1. Now, of course, we see 3 and 6 here. So, immediately I'm going to divide by 3 because it's clear. So this would give me 2 equal x squared times x squared plus 1. And remember, we have to solve this equation. It means 2 equal x4 plus x squared. And as you guys know, solving is factoring. So this will give me, I cannot solve this way. I have to set it this equal to 0. Okay, that's the only way we can solve. And now we try to factor. Even though it's x4, but this is a simple one because I have x4 and x squared. So this basically should remind you an equation of this form, where the z is x squared. So let us factor it out. Can you guys see the factors easily? So it's going to be x squared because I have that. And this is a minus 2, so it's going to be 1 and 2 minus and a plus. Okay, am I right or I'm goofing? It should be plus 2 and minus 1. Let me double check. x4 plus 2x squared minus x squared minus 2 equal to 0. So this would give me, this term here is always not 0 because you're adding a 2 to it. So this would give me x squared minus 1 equal to 0. X is plus or minus 1. So whenever we have a problem, a problem like this, most of the time we have to find the intersection point. So we figure out the interval we need to divide. So that's the interval we need to divide. So that's usually step number 1. Step number 2 is we have to sketch the curve. But in this particular problem, they gave us the curve. And they told me that this is the upper curve from here, and this is the lower curve. So we have that piece. Step number 3 is the way I will ask you the problem is I will ask you to draw a typical rectangle and find its area. What am I talking about? So question number 2 is draw a typical rectangle. Typical rectangle. Label it and find the area. Okay, so that will be usually the question. So what do I mean by that? It means the idea is we take the interval minus 1, 1, we split it into pieces, and we cover this region with a little bit of rectangle, and we add the sum of the rectangle. So typically it means instead of taking every rectangle and dividing it, I want one of them. So I can put here, that's a typical rectangle. I'm going to call it xi. And these are the rectangle that I am covering my region with. This is my typical rectangle. What do I mean by labeling it? It means what's the length of this rectangle? And what is the width of this rectangle? So this will be my delta x. These are the little subdivisions. And what's the length of my rectangle? That's what I mean by labeling it. The length is, if I call this point down here, xi, this is 6 over xi squared plus 1 minus the value of the function down here. That's the length of the rectangle. So when I'm asking you to draw a typical rectangle, it means I'm asking you to draw this rectangle. The length is the upper value, because this is xi, so this is the upper value minus the lower value. The width is the little bit of the delta x. And the idea is I'm covering this region with those rectangles from top to bottom, top to bottom, top to bottom. That's really the idea. So when I'm asking you to draw a typical rectangle, that's really what I want. And then find the area. So typical rectangle, what do I mean by find the area? Means you tell me what the length is. Plus 1, that's the upper value, minus the lower value. That's the length. The width is the delta x, and the area. The area of every rectangle is the length times the width. That's the delta x. X, Y, Z. So every rectangle, that's the picture we do it. Then question number 3 is going to be write the Riemann sum. Write the Riemann sum that approximate the area. That approximate the area. This stage, what I'm thinking about is all those the sum of the area of those little rectangles. These are what we are approximating the area with. So the area is almost equal to. That's the Riemann sum we're talking about. Now I am adding the area of the rectangle, of those little areas. Times the delta x. So the Riemann sum, it means I'm summing the area of those little rectangle, and that's really what I get. The final question is, set up the integral and evaluate the area. To find the area and evaluate. Okay. So what is the integral? So the area is, the actual area, is what happened to the sum of the area of the little rectangle when the number of subdivision becomes very large. It means it's the limit of those when n is large. When n is very large. Now we're going to write the integral that corresponds to that. So this is my area, that's the integral. This is 6 over x squared plus 1, which is the upper, minus the lower. And now the limit. What are the limit of integration? The limit, whenever you want to find the limit, you ask yourself the following question. To cover this region with rectangle, which interval I need to subdivide into pieces? To cover it, we have to subdivide the integral from -1 to 1. But that's how we are going always to find the limit. What should we divide into pieces to cover? So from -1 to 1. Okay. And now evaluate, and now it's a matter of finding the definite integral. Okay, so that's the process I will ask you to use in some of the problems, so to make sure we understand the whole concept. So now let us evaluate. Okay. Integral from -1 to 1 of 6 over x squared plus 1 minus 3x squared dx is equal to. So we always remember that's the upper value minus the lower value. That's what gives me the length. Equal to. All right, now let us evaluate this. So that's a definite integral. And let's see if it's easy to evaluate. This one. Do we know the antiderivative of this piece? Now I go back to you. What's the antiderivative of this one? That's the arc tangent. It's 6 times arc tangent x minus. So whenever we have to integrate, we look. Can we do it? What's the antiderivative of 3x squared? 3 is a constant. Antiderivative of x squared is 1/3 x cubed. X cubed over 3. This is evaluated between -1 and 1. Okay, very good. So now, before we evaluate, I don't think you guys like those. So I'm going to put 3 arc tangent x minus x cubed evaluated between -1 and 1. And now the evaluation part. 6 arc tangent 1 minus 1 minus 6 arc tangent -1 minus -1 to the power 3, which is a -1. So finally, let's get 6 times. Again, what's arc tangent 1? What's the angle whose tangent is 1? Quickly. What's the angle whose tangent is 1? I want quick answers, guys. 45, and we don't use 45. What do we use? Calculus does not like, as I said several times, does not use degrees. -1 minus. Arctangent -1 is minus pi over 4 minus -1 plus 1. So finally I get 6 pi over 4 plus 6 pi over 4. Give me 12 pi over 4 -1 -1 -2, which leaves me with 3 pi -2. End of the problem. Okay. I'm going to do one more problem and then we proceed. So now suppose we tell you it's an easy problem, but let's understand it. Find the area of the region bounded by the graph of y equal x squared minus 3x, y equal to x. So there is no graph. I did not give you a graph, and that will be a lot of time. I will not give you the graph. You will have to be able to do it. What will be the first step in solving this problem? Not the second, the first step, quickly. Draw, exactly. First step, draw. I have no idea what they're talking about. I don't know what my upper curve is. I don't know what my lower curve is. I don't know anything about the region. So the first step is we have to draw. All right. Y equal x is easy. That's the line. I don't have problem with that. So this is y equal to x. I know that. Y equal x squared minus 3x. Also, we should be able to know this. This is, we know it's a parabola. And it's parabola going up. And one way to graph it is, for me, that several, one way is find the zeros, if we can. So on the side, watch what I'm doing. I'm trying to find the zeros. Means x times x minus 3 equal to 0. So we have a 0 here, and we have the 0 here. So my parabola is gonna go, that's the natural way, like that. So that's really my parabola. So step number 1, there is no step number 2. I mean, the step number 1, always to graph. So this would give me that this is x. So this tell me immediately that's my upper curve because we need it. And this is my lower curve, which is x squared minus 3x. So always step number 1, sketch and sketch. Now, step number 2, we have to find which interval we have to cut into pieces to be able to cover the region. So this is my region all the way up to here. So I need to find the intersection because this is the interval. I need to cut into pieces to cover my region with a rectangle. So immediately the intersection point. So we set x squared minus 3x, the y's equal to each other. And the only way to solve is the right side to be 0. So I have to bring this here. And then factoring. I get x equals 0, x equal to 4. And now I check. If I put 4 here, I get 4. If I put 4 here, I get 16 minus 12 equal 4. So if x equal to 4, the y's are equal. So this is my 4. Okay, so now I have my limit very clearly. Step number 2 is we're going to draw a typical rectangle and actually label it. So typical rectangle, it means I need to cover this region with a rectangle. So my rectangle will go from the bottom curve to the upper curve. So this is what I call my little xi. And the rectangle I'm going to cover my region with are very, very thin rectangle. So this is the rectangle I'm going to use, typical rectangle. This is the little delta x. That's the width. We want delta x to be very, very small. And the length is from here all the way to here. That's the length. So the length is, if this is xi, it means this point right here is the value of the function. That's where we're getting the length. And if this is xi, it means this here is xi. That's what I'm getting the length from. So the length is going to be how much we have from here to here, which is the upper value, as we said last time, minus the lower value. Okay, so step number 2 is the typical rectangle. Then the length of it is the upper value minus parentheses the lower value. The width is the little bit delta x. This is the one that you want to be very small. The area is the length times the width. The width is the delta x. The length is that. So that's my typical rectangle. That's what I'm covering the region with. Now finally, the Riemann sum that will approximate the area. So the area is, this is area of typical rectangle.
Professor, I have a question.
Of course.
So does it matter which one gets subtracted? Does it have to be the lower one? Or does
It's
it have to?
always the upper minus the lower crucial.
Okay.
You need a length. It's a length. If you take lower minus the upper, you get a negative number.
Okay, I
Okay,
gotcha.
let us assume this is 4 and this is minus 1. It's 4 minus minus 1.
I see. Okay, that makes sense.
Crucial, crucial. If otherwise you will doing minus 1 plus minus 4, which is wrong. It's always the upper value minus the lower value, always. Is that clear? Important.
Yep,
Yeah,
exactly.
absolutely. Absolutely. So now the area of the region is almost equal to the sum of the area of this little rectangle. At this stage, even though I don't draw it because it's become tedious, I'm adding those little areas. So that's really my thinking right now. That's when I'm writing this sum. I'm not simplifying just to remind you what I'm doing. The upper value minus the lower value times delta x. And finally, the area. At this stage, the formula for the area is becoming fairly trivial. at this point, right, it doesn't really matter. Good question. It doesn't really matter because they all will become close to the actual area. Take right point, take left point, take midpoint. It doesn't really matter. Okay. So finally, what's the area? Is what happened to those sums when n becomes very large. Parentheses, crucial, the length times width. I equal 1 to n and goes to infinity. And now I'm going to write the integral. Write this as an integral. That's the following integral. The function is x, which is the upper function, minus this, the lower function, dx. Limit. Whenever I need limit, I go back to the picture and I say to cover the region with the rectangle, which interval I need to subdivide. So even though I know all of you know it, but I usually go back. I have to divide the interval from 0 to 4 because I'm covering this whole region. So it's going to be the integral from 0 to 4. So that's the area. And now it's a matter of evaluating. At this stage, I start simplifying a little bit the inside because we have to integrate now. So this inside here, if I evaluate it a little bit, simplify it, not evaluate it, it's x minus x squared plus 3x. So this is for x minus x squared. At this stage, I'm just doing the simple simplification. So finally, I would get equal to. This is a simple integral. There is no substitution. There is nothing. It's just a very basic integral. For x is 4 times a half x squared minus x squared is 1 over 3x to the power 3. So finally, I will get the value at the upper minus the lower. At the upper, I will have 2 times 16 minus 4 over 3 divided by 3. The lower, I will have 0 minus 0. So finally, I will get 32 minus 64 divided by 3. And I will stop right there. Okay. So to find the area between two curves, if the graph is not given, step number 1, we find the graph, sketch it. We have to find the intersection point. And then we're thinking a little bit about the process. We draw our tiny rectangle, our what we're calling a typical rectangle. We label it. What's the length of a typical, which is the upper value minus the lower value times the little delta x. We add those and we get the integral. Any questions so far? Okay. Now, if I don't ask you all the details, you usually can go to the formula verbatim. But if I ask you for details, you have to do all the details I'm asking you for. Questions so far? Okay. Now I'm going to give you the following problem, and we're going to think a little bit about it. So I'll probably write the problem on the board. I meant on the piece of paper. All right, here we are. Find the area. Find the area of the region bounded by the graph of x equal y squared and y equal x minus 2. Okay, so find the area of the region bounded by the graph of x equal y squared, to be very careful here, what I'm giving you, and y equal x minus 2. So step number 1 is what? Quickly. What is going to be?
Sketch.
Sketch. I have no idea what else to do. All right, so we're going to sketch. Okay. First, y equal x minus 2. All right, let me sketch this. This is a straight line. The intercept is at minus 2, so it's down here. And the slope is positive, so this is my line. Y equal x minus 2. Okay? Then x equal y squared. Be careful here, I'm giving you x in terms of y squared. So what's the graph of x equal y squared? How does the
Can't
graph?
you
What?
can't you rewrite it as y equals plus or minus the square root of x?
Exactly. So this is gonna give me y equal plus or minus the square root of x. It means for every for every x, I have two y's. So this is gonna give me y equal root x and y equal minus root x. So y equal root x, that's y equal root x. And y equal minus root x, that's y equal minus root x. So it's basically the parabola, just you move it around. So instead of having a parabola like this, you have the same thing, but the axis of symmetry is the x-axis. So this is the graph y equal root x. Okay, so this is the top, this is y equal root x. This is here, y equal minus the square root of x. And this is the line y equal x minus 2. All right. Now the intersection point, as you guys know, we need the intersection. I will give you the intersection and then I'll tell you how to find them because we're gonna solve it then. So this is going to be 4, 2. So if I plug in 4 here, I'm getting 2. That's correct. And this point here is 1 minus 1. Okay. And now I'm asking you to find the area in between. All right. What's the top curve in this problem? To find the area, we have to absolutely know what's my top curve and what's my bottom curve. What's the top curve in this region? This is my region. What's the top curve? All of you.
The square root of x.
Square root of x. Do you agree with your classmate? Okay, if I take my rectangle here, root x. I take my rectangle here, root x. What's the bottom curve? What is the bottom curve? Y equal x minus 2. Y equal x minus 2 with a question mark. Keep looking at the picture.
Is it both root x and x minus 2? Is that the
Exactly, exactly,
okay.
exactly. There is no one bottom curve. Okay? There is not one of them. Let's look at the picture very carefully. I'm going to split like that. Did you guys see where I split? This is the one. From here to here, the bottom curve is minus root x. The upper curve is root x. Am I correct? I want all of you to understand the picture. What if I'm right here? If I draw my rectangle, so I don't really have a typical rectangle. The formula for a typical rectangle is changing a lot here. The bottom curve is y equal x minus 2. The upper curve is square root of x. So the top curve is not changing. So this is really staying the same across the board, but it's my bottom curve, which is absolutely changing. So let's write this down. Let's see how I'm gonna write it. So let us note. If x is between 0 and 1, where did I get the 1 from? This is the intersection point here, 1. So it means right here, this is 1. If x is between 0 and 1, then the upper curve is the square root of x. The lower curve is the minus the square root. So the bottom curve is changing, and that's really what's happening here. However, if this is 4, mean this point right here is 4. If x is between 1 and 4, So that's really what's happening. And then the upper curve is always the square root. It's the lower curve, which is going to be x minus 2. Okay, so typical rectangle, when I'm finding the area of this typical rectangle, I really have an issue. I don't have a unique formula. The formula is changing with the domain. Okay, so in this problem, I'm only going to ask you set up the integrals to find the area. I'm not asking you more detail. So the question is set up the integral to find the area. What do you think I have to do in this problem? What do you think I have to do to find the area?
Set up an integral from 0 to
Add into
1,
different
from
intervals.
1 to 4.
Absolutely correct. We have to add the integral. So I can call this region D2 if you want to call it. It's really up to you. And this is, sorry, this is the region D1. So it's going to be equal to the area of D1 plus the area of D2. Okay, now what's the area of D1? The first D1 from 0 to 1. That's where the limits are so important. And in this scenario, my upper curve, so when I'm taking my rectangle here, the upper curve is going to be the root x. My lower curve is the minus root x. So that's really my upper curve. And this is my lower curve. Always upper minus lower, or you get a negative number. For the second one, my integral is from 1 to 4. And my upper curve here is the square root of x. My lower curve here is the x minus 2. Okay, so to be able to, so because I don't have a unique upper and a unique lower, I have a unique upper, but my lower is changing. I have to split my integral into two pieces. So now this will give me, I will not evaluate the whole thing, but just I'll get you going. Square root of x minus this. So basically that's just 2 square root of x dx plus the integral from 1 to 4 of root x minus x minus 2. And we have to really evaluate two integrals. So the first one, I will not finish. I will just make sure you, root x is x to the power a half is 1 over a half plus 1. So it's 2/3 x to the power a half plus 1, 3/2, evaluated between 0 and 1 plus. Between 1 and 4, this is 2/3 x to the 3/2 minus a half x squared minus plus 2x equal, you guys finalize it, I will not finalize it. Okay, so whenever we have a region, we have really to be critical of the region, and we have to see, okay, what's really going on. Okay, questions before I proceed? All right. So my question is, sometimes I have to split a region the way I did it. I have no choice or whatsoever. But sometimes I can go around this process and not have to split it into two pieces. And so the question now is, how can we go around taking two cases? So question is, sometimes I can't, and you will have a problem where that's the only way out, but sometimes we are. So the question is, how can we go around two cases? Around splitting. And the idea, which is in you here, the idea is area between two curves. So now what we're going to do is we're going to find the area between two curves, the same problem, but instead of covering the region with those vertical rectangle, we're going to cover them with horizontal rectangle. So that's what we are going to do right now. So area between two curves. Using what we're going to call horizontal slices or horizontal rectangle. Or integration with respect to y. Right. The way we did it before, we actually took vertical rectangle and we said that we integrated with respect to x because the variable here is x. Now we are going to learn how to do the same problem, but we're going to integrate with respect to y. So before I do that, I need two notes. The first note is the following. Right. Horizontal length between 2 points. So first, last time we did the vertical length between 2 points, and we said it's the upper minus the lower. Now the horizontal length. So I'm going to ask a very straightforward question. Suppose this is A and this is B, and this is 0 right here. What's the length from here to here? Quickly. What's the length of this interval? I'm reading chat B minus A. The right value minus the left value. All right. Suppose now I'm going to put 0 in between. I'm going to put A here and B here. So I can change them. Again, my question is, what's the length from here to here? Try to remember how I thought about this problem previously. Remember, A is negative. A is negative. B minus the absolute value of A. This is correct. Because now, it's equal to. No, sorry, this is not correct. My apology. B minus A. So it should be B plus the absolute value of A. All right? So to make what Rocco said correctly, it's B, it means this, and plus that. But this is the absolute A. That's to make what Rocco said correctly. So it's B plus the absolute value of A. But now what's the absolute value of A? The absolute value of A is not A, it's minus A. Because let us say A is minus 3, then its absolute value is not this, it's minus 3. So plus minus A. It means B minus A. So the length is, the vertical length is always the right value. So the vertical length, sorry, the horizontal length is the right value always minus the left value, regardless what the scenario is. So for vertical is the up minus the lower. For the horizontal length is the right value. You take away the left value. So, and this makes sense. So if I have any two value here, so suppose this is -1 and this is 4. So the distance from here to here is 4 minus -1, which is equal to 5. That's exactly what I am saying. Now, a second note is the following. Second note is, let us recall something. I'm going to ask very straightforward question. Suppose I have here a function here. Here, Suppose I say y is x squared. It means here I'm going to give you y as a function of x. It means if I know x, I know y. A function of x. So if I draw this, we all know how to draw that. So what does it mean? Y is a function of x. So it means that, let us say this is 2. I give you x equal 2. And I go all the way back to the graph. The formula here, or the equation, if I know x is giving me the y. So this point is 2, 4. But what is the y? The y is the vertical distance from here to here. So if y is a function of x, it means if I know the x, the formula is giving me the vertical distance from the x-axis to the curve. That's really 2, 4. So when in class, when I will put something like xi here, and I go back to the graph, the vertical distance from here to here is going to be, what's the vertical distance quickly? I call this xi. The second coordinate is xi squared. It means the distance, the vertical distance from here to here is the xi squared. Okay, that's really how we base the formula for area between two curves. Now, part 2 is we're going to have a situation in this course where instead of giving you y as a function of x, we're going to give you x as a function of y. Okay, so that's the situation we're going to be working with. So now I'm going to give you, let x be equal to y squared. It means x is a function of y. Means in this scenario, if you know y, the y component, this formula here will give you the x component. Let us understand this a little bit. X equal y squared, we just drew it a minute ago. I think is exactly like this parabola, the one I had before, and you just rotate it. That's x equal y squared. So what does it mean? It's a very simple question. Suppose I'm giving you y. Now I'm giving you the y. And I go all the way right here and I hit the curve. So this time I'm giving you the y. What is the x? Quickly. What is the x?
4.
4. That's the x. So if I know the y, I know the x. Geometrically, what is the x? What's the 4? Is this horizontal distance from 2 to the curve. That's really the 4, this horizontal distance. So if y is a function of x, the y is the vertical distance, and this is giving me the horizontal distance. So if I call this point, I don't know, y, or yi, and then I go from here to here, I hit the curve. What is this horizontal distance in terms of yi? So from here to here, how much do we have? Back to you. If I have 2, from here to here, you have 4, because you plug in 2. If instead of 2, I just be a little bit abstract. I put yi. How much do you have from here to here? Okay, if you cannot answer, I'll pick another number.
Y.
No. Suppose I put here 5. How much do we have from here to here? Remember,
5 squared.
what?
5 squared.
5 squared, exactly. It means this is, I have 5 squared. But in the graph, what does 5 squared represent? It's from here to here. This horizontal distance. This is the 5 squared. Is that clear here? Now, what if I let's move in a way a bit abstractly. What if instead of 5, I put yi here? Why not? What's going to be this distance from here to here? If this is yi, it means from here to here, I have the yi. That's what the yi is. So if this is yi, it means this point, the x, is given by this formula, yi squared. Means from here to here, I have yi squared. So if x is a given a function of y, it means if I know y, that's why I know y. The horizontal distance from the y-axis till I hit the curve is the yi squared, is whatever x is as a function of y. Is this making any sense? Questions? Right. So why we are talking about that at this stage? What we are talking about. The reason we're talking about that is the following, is and I know that I am out of time, so but I'll prepare you and tomorrow I'll go from there. So now you don't have to write. The idea now, if you have two curves, but in this time, instead of giving you x as a function of y, we're giving you y as a function of x. And the question is how to find the area between the two curves if the two curves are not y as function of x, but x as a function of y. And the idea now is we're going to cover those by those types of rectangle, by horizontal rectangle instead of vertical rectangle. Okay. All right, I stop at this stage. Please make sure to do the homework for tomorrow. Do you guys have any questions? Any questions before we stop? Okay, so as you remember, as I told you, I have office hours. Please feel comfortable to show up to my office hours and please do the homework. It's absolutely crucial that you do the homework. Okay, I don't really use Pearson. You guys do the homework, write it, and you ask me questions from it. All right, and when we go to class, hopefully eventually, then I can see what you guys have done. But for now, do the homework, write it down clearly on a piece of paper and ask me questions tomorrow how to do them. That's how I work. Any other questions beside that? Okay, so stay warm and you have no excuse not to do your homework. You are at home. And I'll see you tomorrow. Bye-bye, guys.
Bye, Professor
Bye-bye,
Elias.
Rocco.
Thank you, Professor.
Thanks. You're welcome anytime.